Welcome to today's IBT ABC UTC Research Seminar. The presentations in this seminar series highlight research work at the IBT ABC UTC's partner universities. Each seminar consists of 40-minute presentations followed by approximately 15 minutes of question and answer. My name is Kathy Kroll. I'm the co-director of technology transfer for the IBT ABC UTC. I would love to welcome you and approximately 700 other registered sites for today's quarterly research seminar. I'm assisted by Jamal El-Kaisi, former FHWA, and Rick Lipdick, Michigan DOT's State Bridge Construction Engineer. Jamal and Rick will be moderating the question and answer session. Our featured project today is Predicting Key Bridge Characteristics Using Machine Learning. It will be presented by our colleagues at the University of Washington in Seattle. Before we start the presentation, I have two events to discuss. First and foremost is the 2026 World Bridge Engineering Conference that is coordinated by the IBT ABC UTC. It will be held in Miami, Florida, December 1st and 2nd of 2026. This conference is co-sponsored by the US DOT and over 32 state DOTs. On a personal note, this conference used to be the Accelerated Bridge Engineering Conference, and it was one of the first bridge engineering conferences that I had the privilege to attend. That was back in 2017 when I was with the New Mexico Department of Transportation. I found such great value in the conference content and the networking opportunities there that I've attended every subsequent conference, and I ultimately, obviously, joined the UTC's leadership team. I feel even more strongly now about the value of this conference because the UTC has added the additional emphasis of the innovative bridge technologies, which has opened us up to cutting edge topics like the seminar today. I can't emphasize enough the value I've found in this conference, as it's helped me keep up to date on relevant topics in our industry and helped me develop really valuable professional networks with truly remarkable people. I really recommend that anyone who has the means register and attend this conference. Here are the details. Registration will be opening soon, likely in February. We'll announce that as soon as it happens. The hotel block is already available for registration. We'll be at the Hyatt Regency Hotel in downtown Miami. For those who aren't aware, this is pretty much the best time of year to be in Miami in December. It's just the perfect weather. And we do have a little overlap with Art Basel, which is from December 2nd to the 6th this year. So Art Basel is an annual massive contemporary art exhibit that takes over Miami Beach and overflows into downtown. So hotels are very likely going to book up quickly. So I would encourage you to book early to ensure that you have the best conference experience by being able to be at the conference hotel with the rest of us. We have not yet set the conference program, and we are currently accepting abstracts for presentations. So don't quote me on this, but I believe there will be 5 tracks with 17 presentations each, for roughly 85 presentation options. This is in addition to the keynote presentations. If you've not already submitted your abstract, the deadline is March 20th. Please get to that. There is a fund to provide limited scholarships for government employees at any level of government. If you're in that category, I encourage you to apply for a scholarship, which covers travel, hotel, and registration. Priority for these scholarships is given to presenters. So consider submitting an abstract for a recently completed ABC project or an innovative technology that your team is working on. So do get abstracts in, and then the scholarship applications are due April 21st. There'll be a limited exhibition hall at the conference. Exhibit booths are still available, but are filling up quickly. If you'd like to procure an exhibit booth, see the website or follow the QR code on the screen for additional information. Lastly, we're accepting award nomination submissions for Innovative Bridge Engineer of the Year, Innovative Bridge Owner Agency of the Year, and Bridge Awards for both ABC and IBT in the categories listed on the screen. The deadline for award submissions is June 30th. Again, see our website and/or use the QR code on the screen for additional information and submissions. I truly hope to see many of you in person in Miami in December for this very valuable and interesting conference. Our only other announcement is that our next monthly webinar will be on Thursday, February 19th from 1 to 2:15 Eastern. The presentation will be Delaware DOT's Accelerated and Innovative Entirely Precast Bridges on US 13 over Blackbird Creek. Kevin Lindell and Nick Dean from Delaware DOT will be presenting. Registration is open. You can sign up now on the IBT ABC UTC website. Before I introduce our presenters, I'll review some housekeeping items. Many of you may know these webinars are recorded and posted on the IBT ABC UTC's website in the section titled Research Seminar Archives. So you can access this and all previous seminars for future learning and to share with interested colleagues. Lastly, this presentation will be followed by approximately 15 minutes of question and answer. The seminar today features the IBT ABC UTC's research project on predicting key bridge characteristics using machine learning. Mark Eberhardt and Joe Cho are professors at the University of Washington, Seattle. Mark is in the Department of Civil and Environmental Engineering. John is in the Department of Industrial and Systems Engineering. We are very happy to have you both here with us today. And with that, I will turn the screen controls over to Mark.
Thank you for giving us the opportunity to make this presentation. It's an exciting time with AI and machine learning and all these new things that are going on. And what I'd like to do is really talk about our perspective on it. And it's not the one of coming from personally an expert on machine learning, but more as the expert of the perspective of someone who's a user. So let me introduce the team. So I'm Jeff Berman, my co-PI, and I are both structural engineering professors at the University of Washington. We do bridge and building research, earthquake research, that kind of stuff. And then my co-presenter, John Cho, is working in industrial and system engineering, and he's, of course, the expert in machine learning. And one of the things I'm going to emphasize today is the importance of working together between the domain experts and the experts in machine learning to get anything done, because the problems really are not automated yet. We're not at the place of having just general learning. The last person listed up there is Julia Lensing, and we'll talk about her in a couple of slides. So we're all at the University of Washington, and I think it's a good place to do this work because there's a very strong expertise in computer science and data science. We do a lot of work on earthquake and tsunami engineering. I've been working on accelerated construction for a long time, and from the top to the bottom of the university, there's a huge emphasis on multidisciplinary collaboration. And I think this project is a good example of that collaboration. One person I want to emphasize is certainly Julia Lensing. She got her original bachelor's from the US Military Academy, got a master's in science at University of Virginia. And then she came to University of Washington to get her PhD to work with John. And this work is really the result of her PhD. And the reason I'm giving the presentation and not her is, as you can see from the next couple bullets, she's very busy. She's a lieutenant colonel in the Army, and right now she's the assistant chief of staff for the 1st Cavalry Division at Fort Hood, Texas. And so she definitely has done all the work and had a lot of input on the presentation itself. And she'll be working at the US Military Academy teaching and doing research when her tour finishes at Fort Hood. So as we go into this, remember, I'm really presenting Julia's work, which John supervised on a machine learning perspective, and Jeff and I supervise in terms of the application. I also want to acknowledge the sponsors. So the funding for this particular project was both provided by the IBT ABC UTC and also the Pacific Earthquake Engineering Research Center. Essentially, together, we were able to provide all the support needed. And then the Washington State Department of Transportation didn't support this particular research, but they provided all the information required to do the research. And as we'll see later, there's an enormous amount of work that was required to be able to even start this project. And we'll get into that more as I go on. Okay, so where we're going to go today. So first of all, let's talk about kind of where this project fits in, what we're trying to do. We'll talk about the data that's involved, and of course that's important. We'll talk about the machine learning methodology, and I'll go over it on a high level. And if you have additional questions, then John will be available there in terms of the details of what algorithms we use and how they worked and what are the principles that they rely on. Then we'll talk about how successful they were at predicting bridge properties. And then we'll talk about, let's use it for a particular application. And because I'm an earthquake engineer, we ended up using it as a method to screen for seismic shear vulnerability of reinforced concrete columns. And then we'll finish up with some lessons learned. And we're emphasizing lessons that are not just specific to this project, but lessons that are more generally applicable to people in our field trying to use machine learning as it's developing and being more and more applied. Okay, so first of all, let's talk a little about terminology. The terminology is changing every year. So this slide is from a very recent paper. Maybe it'll change in the next few months. There's different kinds of things. Machine learning is a kind of a catch-all. It turns out that we did some of that, and because we did some language models, maybe it's artificial intelligence on top of that. These terms can sometimes be used interchangeably. But the point is, of course, is using these algorithms that people have developed to look at data or images to try to extract valuable information, and in our case, to support decision making. So we've heard about all the time. I mean, I use it when I'm trying to do any kind of home repair. I go on to ChatGPT. I ask them how to do something. I ask them how to do programming or something like that. And of course, the examples which are best known are these large applications where we use tons of data. And so I've taken this particular example, and you can see here, this is a paper on looking at faces, and you can see they're looking at about 3.5 million identities, different people, and they've collected 260 million faces. And they're going to train their algorithms on, for what is for me anyway, a huge amount of data. That's not us, right? And so 260 million, that's not kind of numbers we're talking about. The kind of work we're going to talk about today is much more saying, yeah, we have large inventories, but getting data is actually quite expensive. So just as an example of this, the United States, according to the National Bridge Inventory, has about 620,000 bridges or so, at least those are publicly owned. I do a lot of work in the earthquake regions. You can see California by itself has 26,000, and my own state of Washington, located up here in the Northwest United States, even our state has 8,500 bridges. So anything you try to do on that inventory can become very expensive, very fast. And there's all kinds of applications of machine learning to bridge management. So some of them that other people have used is certainly for structural health monitoring. And one thing that comes out of that, of course, is that it would be great to have information about 8,500 bridges, but the expectation needs to be extensive on each bridge, and it's expensive to put in. And in general, which is common for civil engineering applications, there's a lot of data interpretation that goes into trying to make sense of what you're measuring or what you're seeing. People have done work in computer vision for inspection. You can imagine drones flying around doing inspection, or people walking around with cameras, getting tons of images and videos. But even when you've done that, you still have to get information about the structure metadata or the main characteristics of the bridge. And then you have to say, well, what am I looking at? What are the states I'm looking at? What am I trying to figure out? And how do I interpret that? And then the third category, which is really what we're talking about here, is this idea that we're trying to predict performance. How can I use these tools to predict something which I can't do as easily right off the bat without having to do all the detailed analysis? And in general, that talks about having some kind of databases that are either available or they can be put together, and then deciding what is performance you care about. And you have to measure that performance in some kind of quantitative way. And then you have to have observations to try to determine what is good performance, bad performance, or the category performance that matters for you. So there's a lot of work going on. But what I think common to all three of these categories is, again, there's orders of less data, less information available than looking at 260 million images. And these relatively small data sets are going to provide particular challenges, and we'll discuss them a little bit as we go through today. So an example of a very common problem, one that's close to my heart, is looking at an inventory of bridges under a particular earthquake scenario. And so you can see on the left side picture, there's the upper Northwest. You can see actually southern Canada. You can see Northern California, Oregon, and Washington. And if the Cascadia subduction zone were to undergo a full rupture, it would be affecting something like 20,000 bridges or maybe something like that. But even the Seattle Fault, which is shown on the right side, where again, the colors are just the intensities of earthquakes, even that is going to affect a large urban area. And if you're trying to figure out what the impacts of those bridges those earthquakes might be, or if you're trying to figure out which bridges should you retrofit first, you need to get a lot more information. And of course, this problem shows up when you're trying to do all kinds of maintenance issues, all kinds of retrofit issues, but just using the seismic one as an example. So where are we then? In general, we're trying to figure out bridge characteristics for either prioritization of retrofit or modernization. And then we're trying to look at for large scale, either resilience, loss, estimation, management, whatever it is. And the idea is, of course, we only have limited information on key properties. We really don't have enough information to make the decisions that we would like to make. And so the question we asked here was really, can we use machine learning to help estimate the properties of bridges, in our case, mainly seismically related? Can we predict those with information that is readily available? And then as an example, we applied that to a real problem, which was seismic screening to try to find whether columns were likely to fail in shear or not. And then finally, in a bigger picture, is to try to provide recommendations to DOTs and other bridge managers to try to see to what extent this technology could help them in their work. Okay, so let's take an overview of the strategy that we implemented in our particular project. So in the state of Washington, again, there's 8,000, 8,500 bridges. I'm showing with the red dots there, those which are Western Washington, which are more likely to be affected by earthquakes. And you can see there's a lot of bridges within the state. It would take a lot of work to try to figure out the properties of every single bridge. In parallel, with the funding from the Washington Department of Transportation, their staff and our staff put together a detailed bridge database of about 800 bridges. And the question then is, can we take an algorithm based on machine learning, which try to predict the properties of that detailed bridge database, so those 800 bridges, by taking only the properties that are available in the bridge inventory. And once that machine once the algorithm is trained, one could then implement it on the full inventory to try to predict whatever we're trying to do. In our case, seismic vulnerability. Okay, so as in all machine learning problems and all, we need to look at the data first. What are we working with? I think all of you are probably pretty familiar with the National Bridge Inventory. It has 116 properties, location, category, clearance, traffic, inspection, funding source, all that kind of stuff. All that stuff is great, but it's pretty much irrelevant to what we care about for seismic issues. There is some structural info, the maximum span length, the deck width, the structure type, material type, and one important one turns out to be, of course, the year of construction. An example of information in the National Bridge Inventory is looking at the bridges for which we had detailed information. Here's a bar chart, and it looks at 5-year intervals going from 1925 all the way to the present. And it's just counting the number of bridges in every 5-year interval based on the construction year listed in the National Bridge Inventory. And we have a distribution that's pretty common in many states, which is the vast majority of bridges were built between 1955 and 1980. And of course, that has to do with the construction of the National Interstate System in the United States. But we care about many other properties. So to do that, the DOT staff and our students reviewed about 800 sets of plans. And that basically means downloading PDFs, looking through all the plans, hoping the information is still there. We were focusing mainly on bridges with columns. And to get that, we had to, first of all, remove all the bridges of those 800, which had single spans. Those had wall piers. Those were pier pile supported. So a lot of bridges has direct supports by timber steel, cast in place, or pre-stressed concrete piles. Those have a very different behavior. And then it turns out some of them were not even listed in the NBI. And some plans were so unclear because they might have been done in the 1920s that it wasn't possible to get the properties. So a lot of the work was actually getting the information to train the algorithm. That's a big part of the work. So by the time we started off with 800, we went through all this filtering we ended up with 478 bridges with columns. And for those, we collected tons of details. And among them, the column geometry, the reinforcement details, the abutment properties, and actually there were about another 100 properties that we collected. All those that talk about exactly what's going on in that bridge. An example of this, for example, is just figuring out what is this type of column we have in there. So this slide shows the number of bridges, again on the vertical, and then looking at the different types of reinforced concrete columns that are out there. So this is after the filtering. This is taking out the walls, taking out the single spans. You can see the vast majority are circular columns, but there's a range of hexagon, oblong, rectangular columns, and even some rectangular columns which have spiral reinforcement, which is a more recent detail. So all that is collected in that detail database, but it's not in the NBI. And one key feature is certainly, if we're going to look at shear failure, is the spacing of transverse reinforcement. So this plot shows the spacing, or sometimes called the pitch, of the transverse reinforcement plotted versus the year built. And this turns out to be really important because this reinforcement is key to providing shear resistance during earthquakes. And as you probably saw the pattern already, if you look at the older bridges, almost every bridge is spaced right at 12 inches. And that's because until about 1971, transverse reinforcement, even in earthquake-prone areas, was pretty much there to hold the bars in place. And there was a specification that said all your spacing will be no more than 12 inches. Since they weren't worrying about seismic failure in shear, 12 inches became the default number. You can see after the earthquake, there's a quick reduction. There's a lot more bridges that had smaller spacing, but because there's delays, right? Some things were designed, takes a while to implement things. This is actually for Washington State, not for California. And you can see there's a period of transition between the larger spacing and the smaller spacing. And then there's the 1989 Loma Prieta earthquake. And you can see after that, all those wider spacings disappear. And after that, the spacing is quite a bit smaller. Okay, so we have essentially the NBI, which provides one level of information for all the bridges. We have the database we collected with DOT to figure out what are the details. And we want to try to get that machine learning framework to learn from the NBI how to predict those details. And there's a lot of details up here. I'm going to purposely not dwell on the details, but certainly John can come back and talk about that more. If you look at the top up here, you can see there's National Bridge Inventory that clean, encode, scale, remove outliers. All that has to do with processing. So some of it we talked about already. Some of it comes down to how do I represent these properties in a way that the machine learning algorithm can understand. And that has to be done both on the NBI side and on the detailed database side. Then it gets put together, and you got to figure out what are the properties you're actually trying to predict. And then one thing that's a little bit new here is that you're going to take, well, what's not new is you take some data, you set it aside for testing, and you take the rest of it for training. But because that database is relatively small, it turns out that how you pick one population versus another might actually affect the results. So because the size of our data set, we literally went through and did this whole thing 10 times. So basically you take 100 bridges you set aside, then you train with 378, and then you do it again and again, each time giving a different set of 100 bridges. And as we'll see later, it gives you different results because it turns out the data set is small enough that the picking of the training set actually becomes important. And then after you've trained your machine, you come down and you evaluate the performance, and you can determine what metrics you want to use to evaluate the performance. So that's the algorithm. Okay, so in this case, we're going to take 4 targets as the features we're trying to actually predict. And it turns out these are important for seismic regions, but I think what's more important now is just to show that how the algorithm can work for these different things you're trying to predict. So one of them is on the upper left-hand side is the columns for bent. So bent is just another word for interior support or a pier. And you can see in that database, the most common bridge configuration has 112. The 112 of those has just one column and 2 columns. And as you go from left to right, it gets smaller and smaller. Second thing is important is really how stocky those columns are. And you can see some of them are super stocky on the left-hand side. and then around 4 to 6 is kind of the most common ranges for bridges. You care about how much longitudinal reinforcement is in there, and we express that as a ratio of the amount of reinforcement divided by the area. Again, another distribution. And then you can see the transverse reinforcement ratio, which is super important because that's again about shear resistance. And you can see there's a bunch of bridges on the far left side. Those are all those old bridges we talked about that have very little transverse reinforcement. And then you can see as you go from left to right, there's a wide distribution, which is based on more modern calculations. Now, I want to put this slide up here and just discuss the trends, not all the numbers, of course. But I want to show this because it shows the kinds of information that you get, and then you have to decide what you want to do with it. So one thing is, in this project, we actually use 6 different models. So decision tree, random forest, support vector machine, gradient boosting, neural network, all those are individual techniques. And then AutoML is a technique which essentially combines all the others automatically and tries to combine them all together to try to get the best results that are possible. And then, of course, you have to find some way to measure what you're doing. One way is a root mean squared error. Another way, of course, is correlation coefficient, R squared. You'll get different results, but of course, you need to decide what's important for you. And then the third one, of course, is that the results you're going to get are going to be depending on what you try to predict. So, for example, the R squared might be very high for something that you know very well, and it might not be so high for another parameter. But something to note here is these are actually listed in terms of the ones which are better or worse. And let me show that in a graphical way. So here is just taking the coefficient of determination, R squared. We're plotting the same information. Here you have all the methods on the left-hand side. You can see that's done for 4 different parameters we looked at before. And if you look at the top ones, you can see that, and they're ordered in how good they are on average. So if we look at that first red circle on the upper left-hand side, you can see in this case, AutoML, which is the one which combines all the other methods, is the best because that green dot is furthest to the right, which means you have an R squared of about 60%. But you can also see there's error bars there. And that's because we've run this algorithm 10 times, and one time it was up at 65% or 62%, and one time it was down at 57%. And you can see as you go through these methodologies, some of them work a lot better than others. You're down here at the neural network. You can see that's a terrible choice because in this case, it goes from 0.12 or 12% to 24%. And of course, what you're trying to, the method matters, but also what you're trying to predict. And you can see the axes are also quite different. You have 60% for columns for bent. It goes up to 40% for minimum aspect ratio. And the worst one is longitudinal reinforcement ratio, where you can see some of them, like decision tree, just gives you basically nothing. Sometimes it actually hurts you. So you care about how you measure, you care about the algorithms you use. In our case, we found that AutoML was always the best, or if it wasn't the best, it was close to being the best. So we use that more in the future. Now, another thing that comes out of these algorithms, which I think is pretty important, is it will also tell you what is important. In other words, what are the parameters in the National Bridge Inventory that contribute mainly to your model? That's important because if you're trying to figure out, first of all, whether the things make sense, you'd like to have some physical understanding. And also, you also like to know what information you really need to be able to do your work. So columns for bent is probably not too surprising that the most important parameter is deck width. Of course, if you have a wider deck, you can have more columns. And so that turns out to be pretty predictable. The transverse reinforcement ratio is absolutely determined by the year built. And we know that from the plot we had before. So in some cases, machine learning is giving us back information we already know. It's just combining it in ways that allow us to make estimates. Okay. Another thing that is valuable, I think, is when you use this combination algorithm, it also talks about how much the other algorithms have contributed to it. So in this case, the names are a little different because they're actually specific programs rather than methodologies. But the AutoGluon project, it uses all of these algorithms. And you can see in this particular case that light GBMXT was the one that was used the most. And for whatever reason, the exit trees MSE on the one on the left are used less. So that combination algorithm also gives you information about which algorithms are working the best according to that auto ML combination. So we've done all that. Now what I'd like to do is just say, that's great. There's lessons learned. It depends on the algorithm. It depends on the feature. We can measure things with different ways. But in the end, as a bridge owner, I think what you really care about is you want to measure things, not because of the correlation coefficient that you care about, but because whatever you develop is actually satisfying your needs. So in this case, we're going to use it to identify where the columns are likely to fail in flexure or in shear during columns. And if you have a background in earthquake engineering, you'll know that columns that can fail in shear will fail brittly, can often lead to collapse of a bridge, whereas bridges where the strength is controlled by flexure have a much more ductile performance. And you can develop, using some simple approximations, a equation called the shear critical column index. It combines some things you know, like the parameters that you know that are common, but it has in particular those 4 circle parameters, which are not coincidentally the 4 parameters that we looked at before. And there the issue, of course, is can I predict not these individual parameters, but can I predict the actual likelihood that a column is going to be shear critical? And so if I go down at the bottom, there's 4 different options. One of them is just using year built. One of them is using just the NBI database data. The next option is to use all your predictions of these individual 4 parameters with the NBA data again. You're basically feeding a machine model into a machine learning model. And then final one is using, the NBI is the best prediction, and the last one is using all the information together. So this plot looks pretty similar to what we had before. Essentially, again, we're assuming you developed your machine learning model to begin with. You're looking at your application. It turns out for capacity demand ratio for columns, you really care about we have 1 column or more as opposed to the number. And we looked at, again, these different options, year built, NBI, or NBI plus best predictions. We only use the AutoGluon approach. That's an AutoML algorithm, because we saw from the previous work that seemed to work the best. And then we tried to predict that capacity demand ratio. And then what we did is we said, well, we don't actually care about predicting necessarily just capacity demand ratio. We care about how can we identify the bridges which are the most vulnerable. So in that case, we're really looking for the worst capacity demand ratios. So we calculated capacity demand ratios for every single bridge of those 478 bridges, and they put them in order, with the idea that what an owner really cares about is identifying the worst bridges quickly and addressing those first. So the output of this algorithm is an order of all the bridges based on the detailed knowledge of which ones have the worst capacity demand ratios, the ones we should inspect most, or the ones for which we should do a detailed analysis earliest. And the question is, does this algorithm allow us to identify bridges faster than if we were just taking bridges automatically and randomly? And so let me take a little deep breath here to explain this plot. On the x-axis, we're looking at the cumulative number of bridges that are inspected. So we're just saying this is how many bridges we've looked at, either by going out to the field or going into the plans and doing the detailed work to get the information we need to do the real prediction. On the vertical axis, we're looking at, given the number of bridges that have been looked at, how many shear critical bridges, or what percentage of the shear critical bridges have we identified? Okay, so if I look, for example, at the assumption that I don't know anything about the bridges at all, and I'm just going to randomly go through and look at bridges. Well, that means, of course, if I looked at 40% of the bridges, I'll have figured 40% of the shear critical bridges. And to get all the critical bridges, I need to go look at every single bridge. So that red line is a random one, which means we haven't done any work at all. And then the blue line is what happens if we actually had all that detailed information for all the bridges. And you can see here, of course, if I want to get all the bridges that are likely to fail in shear, I have to keep inspecting them. And of course, I have a 100% success rate. And it looks like I have to look at about 23% of the bridges to get my 23% of the shear critical bridges. And what the machine learning does is it basically provides you these lines in the middle. And those are two versions of the machine learning algorithm. And the point is that if I were to take, just trying to figure out the 20% of bridges which are the worst, the ones that are still critical, by taking my red line, that's my 20% bridge line, I only have to look at about 9% of the bridges. So essentially it's an acceleration of about twice. I have to look at about half the bridges. I'm figuring out shear critical bridges twice as fast as I would if I were just looking at randomly. And if I go higher, you see that that acceleration actually is not as fast as I go down the inventory, because now I'm now finding bridges that are more close and more marginal. And you can see here that at this point, to find 80% of the bridges that are shear critical, I have to look at 60%. So my acceleration is not all that high. And I'd argue that to a certain extent, this tool tells you you need to do something else. But looking at the data, we know that one of the things we can get actually relatively quickly is the span to depth ratio, which is important for that column. So this machine learning doesn't just give you the answer, but it kind of gives you the direction, which is, oh, I need additional information to actually make a good guess. So we looked at what happens if we actually knew the length of the column and the diameter. So now you imagine going into the database, look at the shortest column, getting the length, getting the diameter, adding that. That's a very quick calculation. And now we get such a new set of plots. And you can see now, if I want to get the 20% or 20% of the bridges that failed in shear, I have an acceleration of factor 3. I only need to look at 6% of the bridges. And you can see at the top here, to get 80% of the bridges that failed in shear, I only need to look at 45% of the bridges. So whether that's worth it to you or not is entirely up to the bridge management and the logistics of what they're doing. But I think machine learning is giving us a good sense of to what extent will this tool help. But to remind you, the NBI was not developed to do any shear critical work. We're really using an almost unrelated database to try to predict something which we care about. Okay, so just to summarize where we are, bridge engineering applications often have data characteristics that differ from better known large-scale applications. And so I'm pointing out is this whole presentation is not about finding pictures of hundreds of millions of people and trying to identify who they are. We looked at 6 machine learning algorithms, and we saw that performance depends on the algorithm. And if you want to do a similar kind of work in your application, you probably have to do that as well. You can't just pick one and run with it. We found that the auto-applied ML, which the brand name is AutoGluon, or the algorithm name is AutoGluon, it worked the best. And to see whether it works for us, we're arguing that it's not really working because the R squared is high or low. It's really, is it working to fit the needs of your institution? In this case, we applied it for identification of shear critical columns. And because what we cared about was identifying the worst columns the fastest, we assessed it not by an R squared, we assessed it by looking at how quickly you can identify the most critical bridges. So from those conclusions, the high level lessons I think that we've learned certainly is you absolutely need a multidisciplinary team. That ML expertise is absolutely needed. You can't just run the algorithm without knowing what you're doing. But also to get the data in the right place, to be able to interpret the data in ways that are physically meaningful, you have to have the domain expertise. So close partnership is absolutely critical to all this. It's better to implement a variety of algorithms because they don't all work the same. Machine learning is just not one thing. It's a lot of things. We also learned that for small data sets, you really have to repeat that sampling because the sampling itself will change your results. And then the last point is that success and whether you should implement something is not just an R squared issue. The question is, does it add value to your asset management? Thank you.
Great. Thank you very much, Mark. That was very interesting. Now I'll invite Jamal. We'll go ahead and kick us off with question and answer.
Great presentation, Mark. We got some questions prior to the presentation, and we got more questions during the presentation. So I'll start with the questions prior to the presentation. The first question, Mark, is could a similar approach be used for correlating chloride penetration based on a chloride profile for approximately 15% of the inventory?
I'm not a
columns.
material scientist, so I can't tell you whether it'll work. The principle certainly would be the same, which is you'd have to have the information about the actual chloride penetration for a sufficiently large number of bridges. And the more information you have, the better your algorithm is going to be. And I would guess that would correlate certainly with the age of the bridge and maybe the traffic on the bridge or something like that. Yes, certainly the algorithms could be used. Whether it would work well or not, I don't know, because that would have to be explored.
Yes. The second question, does any machine learning software need to be pre-installed?
Yes, depending on their familiarity with the machine learning tools, they could pre-install machine learning related software to get these things done. In our case, we used Python, like Python for everything for this project.
So Python need to be pre-installed here. The third question I have, what type of bridge inspection data can we start collecting today to help train the machine learning algorithm?
So it depends, again, what you're trying to predict. If you're trying to predict seismic vulnerability, for example, I talked about adding the span to depth ratio. Well, you could ask the inspectors just to add that on it, because it might be on the plans, but because of the impact of the soil surrounding the columns, it might not be as trivial as looking at the plans. So you can certainly get the information, but you need to make sure that the inspectors are collecting just information you need for your use, right? To a certain extent, a lot of things which were in the vulnerability of shear depend on the reinforcement inside and transverse and longitudinal reinforcement. Neither of those are going to be visible to an inspector. And I'm sure you could do it with, you can detect the location of the transverse reinforcement with a magnetic detector, but then now we're asking a lot of information. You might as well look at the plans. And so I think the answer is, can the inspection tools, the inspection procedures provide you more data? Absolutely. In fact, I'd argue that this kind of machine learning can maybe be used to help you figure out what information you actually need to make better predictions.
Yes, and the next question will be related to the third question. Will this technology have the ability to data mine inspection notes to detect trends and deterioration of hotspots?
So that's a visioning kind of thing, right? So for example, we at first said, oh, maybe we could get machine learning to look at the actual plans rather than having us hire people to work and draw down the plans. It turns out it's very, very complicated because some of the plans were done back in the 1950s and 60s. There's not really standard drawings. And so I would imagine, and maybe John can jump in here as well too, that it depends on to what extent information is kind of presented in a systematic way. So in the DOT, we have a lot of standard details. My guess is that if you give a PDF to the right algorithm, it can identify certain standard details that appear over and over again. But if you give it a drawing that's blurry, that is missing pages, I think that'd be more of a challenge. And of course, who knows what they might do in the future, right? In the future, they might be able to do a lot of things we can't do now. But John could probably provide you a more technical answer.
That was a great answer. Our machine learning pipeline / framework that we discussed here today are not going to directly address that needs. So as Mark noted, like nowadays, vision language models are evolving very fast. So in perhaps a few years later, it might be possible, like those models, vision language models might be possible to handle very, very different plans, like plans that were written many years ago. But as of today's technologies, yeah, it seems quite not feasible.
Great. The fifth question here, what were the procedures or the steps taken to verify the model and eliminate hallucinations? And I think you went over that during your presentation, if you want to add any more.
There's a couple steps. One of them is the data was put together, and when results came back that were very different, the trends weren't the same, Julian Light came back to us and we'd go back and check the drawings. I think we found 2 or 3 data points where even though we had been double checking everything, the data was wrong. So data cleaning is certainly part of what's going on. And the second thing, which I think is talk about hallucination, is that's one of the reasons why it's important to sample that data a number of times. Because if you pick 100 columns out of the 478, depending on how lucky or unlucky you pick those columns, you might train it against something that doesn't make sense. And when you apply it, it doesn't work, or it works too well.
That's true.
I think one way to avoid hallucinations is to do it a number of times where you're randomly picking the sets.
Yes, verification is pretty important to finesse the model.
Yes, and you don't want to overfit, right? If I always have the same database, I can pretty much overfit it. So it always.
The next question, Mark, how were the key structural characteristics extracted from the structural drawings of a large number, which is 796 bridges? It sounds labor intensive.
Yes. So it was labor intensive. A lot of it was done originally by the Department of Transportation. Had some interns they hired for the summer. We followed up with, I had 4 undergraduates who worked on this. And I think it is labor intensive. And that's almost the point, which is it is labor intensive. So you don't want to do it for 8,000 bridges. Having done it for 800 was plenty. And it's good for the students because they get to understand what bridges look like and what plans look like and how to read plans. But I agree with the questioner. It is extremely labor intensive. That is a reason why we're trying to find a way not to have to do that for the full inventory.
Good. The next question is, can this be used in all concrete bridge construction?
No, it can't because, well, to the extent that another state has the same distribution of properties, maybe. But if you look at the history of earthquake engineering in particular, different states have done very different things. And so we should not assume, the nice thing about theory is that you kind of have some physics behind it, you can extrapolate that. That's one reason I love it. Because we don't have an equation that's based on physics, that means that what we develop is entirely based on the inventory on which it was trained. So it can be applied somewhere else as long as the inventory is similar. And you'd have to, at the very least, collect information for several hundred bridges and try it before you determine it was okay for your own state.
Yes. The next question is about cost. What are the cost implications of this technology? Does it save money for bridge owners?
My sense is that it depends. Again, the answer depends on what you're applying it to. In this case, I'm not a salesperson who's trying to sell the algorithm as this is a way you should do seismic screening. This was an exploration of the potential, right? And so your algorithm is going to be more and more helpful the extent to which the database provides you information that's relevant to it. And we purposely picked the NBI that has no seismic information, and we purposely tried to apply something that was far away from it. My expectation is that the more you apply something that's closer to what the original data was available for, the better it's going to be. And some people have, for example, looked at trying to predict the condition of bridge decks using machine learning as well. And machine learning does have things like, NBI does have things like not only when the bridge was built, but when the deck was redone, there's some management things in there. So that might be a little bit more successful. But the answer, I think, it depends on to what extent the data is what you need, but also the extent to which it's expensive to get that data. At some point, you might say, I'm going to hire someone to get the bridge properties for 8,000 bridges. And I'd rather do that because then I have the actual numbers. But that's, it's hard for us in our project to evaluate the actual costs. That's the managers themselves that have to figure that out.
That's right. The next question, can this technology extract all strength categories needed?
So, the NBI doesn't have things like column size or reinforcement ratio. And so trying to get the flexible strength without knowing the size of that column is going to be challenging, right? So my guess is that one of the things that worked for us was that we're trying to get a ratio. So we had a non-dimensional ratio. So what we cared about wasn't whether the column was large or small, but to what extent was it highly reinforced versus low amounts of reinforcement for longitudinal and transverse. And you can imagine there'll be trends based on years, based on those ratios, as opposed to predicting the actual strength. And I'd be skeptical about getting a strength because we know a 6-foot column, diameter column is going to be stronger than a 2-foot diameter column now.
The next question is, how could you predict the key structural characteristics of bridges using NBI data, as the NBI data does not provide structural dimensions like you mentioned earlier?
That's right. In fact, that's exactly the point, that we were trying to see to what extent can we find essentially hidden trends. Because we know the NBI was doesn't provide what you want. In fact,
That's right.
I think we're applying it in the most ambitious kind of way, which is to take data sets which are on one level almost unrelated, but then you get things, I mean, to get the details of things like columns with single pier are in one level bending and ones with multiple columns have double bending. That has to do with bridge deck. So there's trends you can find that are indirect. But again, that's why when you go and look at the inspection, we weren't able to find things perfectly. We're just able to accelerate things. And so I think the question is perfectly right, which is this was an ambitious place to try to apply machine learning.
Yes. The last question, Mark, is not related to your presentation. It's just a general question. Are there public bridge-related database available beyond the NBI inventory? Should this data be made public?
Yeah, so there's issues about access to this. And so, for example, all the plans are certainly not made public. So what we're doing is we're going to make information, we're not going to make it available as in actual bridges, but we're going to try to find some anonymous way to provide some of this information such that it's not traceable back to individual bridges. And you can imagine, in fact, there's probably 20 bridges in the state of Washington which we didn't have access to because they're viewed as being national security of importance. Even for standard bridges, most DOTs don't want to just provide that detail out there without some kind of control on who sees it. So I think the answer is we'll provide enough information so people can work with algorithms, but not to provide the all the data, because I think that would violate our agreement with the Washington Department of Transportation.
Now we have more questions that Rick will be covering that came in during the presentation. Rick?
Yep, thanks, Jamal. And Mark, I have a few questions that come in through the presentation, and I want to compliment you on all that highly technical stuff going through it. That was pretty good. But one of the things that is asked, okay, can you take you got the current state of technology, or given the current state of technology and data acquisition, can you supplement the NBI data with, say, satellite imagery and stuff like that to use it to help identify the key attributes? I mean, obviously you focused on using the NBI, but there is other data that could be, I'm assuming, pulled into it. So.
Well, for sure. So I mean, I do work up here also on tsunami inundation, and to figure out topography and heights of decks and things like that. Absolutely, satellite information is critical for that. There's been work that's been done at UCLA where they're using essentially street view information. So they go through Google Street Images, and you all can find your house on that. You can also find a bridge on that as well. And you could also, that's one of the reasons we took span of depth ratio as something which we could collect in addition, is because there are other projects that are using street view cameras just to go and you can figure out the height of the column from that. Looking in the bridge gets more complicated because there's really no technology that's allowable to do that. But absolutely, there's that potential. Of course, people have been using drones for some, you can't do the whole state of Washington, but if you want just a community, you can certainly use drones to extract some more information that you need.
Yeah. So, and I guess building off that a little bit, so feature selection is very important. Obviously, the different bridge features, and I guess how did your team determine what was the critical features and narrow them down?
Yeah, that's a great question, and that gets back to the multidisciplinary team, right? Because if you have an NBI database with 116 different features you're using, some of them are things like longitude and latitude, for example. And so we said, well, we don't want to train something that is based on the actual pattern, which might be there, by the way. There might be that northern parts of the state, for some reason, they have different properties, but that's going to be hard when you try to generalize that.
Sure.
So some of them were taken out just because we don't want that information to actually be in there. But also the algorithm was run repeatedly, right? And so Julia would come back and say, here's some features which I think we should take out. What do you think? And so part of it was her looking at that feature importance. I had that slide that showed how much important the features were. And so features which were less important were likely to be dropped. But also that was usually done after talking to us and saying, can you see why that might be important? And so without belaboring too much, but one example was, it turns out that the bridge deck is one parameter, but also the width of traffic is another parameter. So sometimes you have two parameters which are almost the same.
Oh.
At least they're highly correlated, right? So at some point we say, well, actually, I don't want to have bridge lane and bridge width because they're actually the same thing.
Yeah.
But then all that is getting back to the machine learning person doesn't know that just offhand.
Sure.
When you see it as a user, you go, oh, of course. So I think it's just going back and forth. We didn't find any kind of automatic way to do that.
Okay. Yeah, there was a viewer said, from my experience, bridge feature detection with ML algorithm usually gives accuracy within 50 to 70% in terms of I'm not sure what RMSE, but the trend is usually accurate. Was this a common observation during the work?
So they're referring to the root mean square error, RMSE, I think. It depends on what you're trying to predict.
Yep.
And so, let's go back to those tables and see the actual numbers. Yeah, it depends very much what you're trying to predict. So some things like the spacing and transverse reinforcement, that is so well correlated with age, you can pretty much nail that. Other things like the longitudinal reinforcement is not correlated well with anything. And that one we had very high RMSEs or very low R squareds. So I think the answer is it depends on what feature you're looking at.
Sure. Yeah, because it's all variable all the way through, right?
Everything is varying, and some of them you can say, oh, I get it. The number of columns is very much related to deck width.
Mm-hmm.
But the amount of longitudinal reinforcement we have in a column, we never found something that was clearly related to something else in the NBI.
Okay, so another one here. From the data considered in this study, example, the NBI data, was the amount of traffic on the bridge and its importance classification considered in the results? And if so, how was that factored, or what kind of weight did that put on towards the importance of the bridge?
So it was certainly originally in the database. It never became an important feature, but some of the features had, some of the parameters had, I think, the band length or something like that, something which I have to go back at the features, look at the details at that. Let me do that right now. I think I'll answer feature importance there. And you can see that there's like length and structure improvement. Oh, here you go, future average daily traffic. And so that one's in it, but honestly, you can see it's doing it. It's the worst one to predict. And
Yeah.
It's there, but then you have to ask, why is it there and why is that important? So it shows up, but whether that's an artifact or not, I don't know.
Sure. It all kind of comes down to how you're going to classify the things, right? As far as what you're getting at. So, all right, the next one. How did your team verify if the shear critical and checking against the model, if the bridge was shear critical and checking against the model's predictions?
Oh yeah, so I didn't include that as part of it, but that shear index was compared to, we have about 400 results of column tests, and we found that was a very good predictor of the likelihood of shear failure. And so I didn't include that in there, but there's actually that, because this talk was about machine learning, not about shear resistance, there's a whole derivation of that, that parameter, and then that parameter, of course, was compared with test results. And you can imagine, given the value of that parameter, you can get the likelihood of shear failure.
Yeah.
Right. So if that parameter is 3 or 4, it's going to be just fine. If it's 0.1, it's definitely going to fail.
Mm-hmm.
And one of the reasons the algorithm works pretty well is that a lot of columns are at the far end of, they're not going to work no matter what. And other columns are going to work. You're not trying to predict exactly that ratio. You're trying to predict whether it's far, if one's going to be 0.1, another one's going to be a 10.
Mm-hmm.
You don't have to be that good at predicting. You just have to be able to distinguish between the 0.1 and the 10.
So the last question I'm going to hit you with here is, the person said, nice presentation, and then said, is there a report or a paper anywhere that goes into that you've worked on or published? I guess I don't know. A lot of these research stuff obviously goes to so.
There's 2 things. There's actually 3 things. One of them is Julia Lensing. She wrote a PhD thesis, and that's available through the University of Washington. If you type in University of Washington PhD theses, put her name in there, you will be able to download the PDF. Now, she did more than just this, but there's a chapter essentially which has that in it. A second thing is Julia wrote a paper which is under review right now. My guess it'll probably appear in the next couple of months because we just got our comments back last week. So
sure.
It won't take too long to get it back out. And then the third thing is we will be writing a report to the ABC Center, and that's basically our next, our final step. And those reports are made public on the IBT ABC website.
Mhm. Yep. Okay. Well, like I said, Marcos, it's an interesting subject, and lots of that data is obviously a big part of the whole thing and digesting it all. So, Kathy, I guess if you had final words to.
Great. Thank you very much, Rick.
Yep.
Thanks again to our presenters for sharing the IBT ABC UTC research work and for your thoughtful responses to the question and answer session. I always call that the secret sauce of our web series. It really lets people be interactive on these. And thank you also to Jamal and to Rick for moderating the question and answer session, and to all the participants for your interest, attendance, and questions. Please join us for next monthly webinar on February 19th, and for our next quarterly research seminar, which is scheduled for April 24th in 2026, and also our World Bridge Engineering Conference from December 1st to the 2nd in Miami. This concludes today's seminar. We thank you very much.